Hello and welcome to this video. In this video we're going to be reciprocating a pre-existing graph. We'll do one example in this video. Given the graph of f of x shown on the grid below, which is this parabola, which is already given to you, sketch the graph of the reciprocal of f of x. It's important to note that when they're asking you to sketch the graph of 1 over f of x, using function notation for f of x also means the output value for the function or the y value. So what they're asking you to do is reciprocate each and every y value found on the original graph. So what effect does reciprocating a value have on that value? This is an important thing to know before you start trying to draw the graph. If the original value is 1, what happens when we reciprocate that number and we take 1 over the original value? Reciprocating 1 gives you 1 over 1, which is still equal to 1. So reciprocating the number 1 has no observable effect. It's the same with negative 1. When you reciprocate negative 1, you get 1 over negative 1, and 1 divided by negative 1 is negative 1. So reciprocating 1 and reciprocating negative 1 has no effect. Reciprocating the number 0 has an important effect. When you reciprocate 0, you get 1 over 0, which is undefined. This will lead into asymptotes in our graph if we have any y values of 0 present in the original graph. For any other value, it's just important to look at how numbers behave. If you take an arbitrarily large original value, let's take 100. Reciprocating 100 gives you 1 over 100, which is 0.01, which is a very small value. Reciprocating 10,000 gives you 1 over 10,000, which is 0.0001, an even smaller value. So what we can pull out of this is that as the original number gets larger and larger, the reciprocal of that original number gets smaller and smaller. Never gets to 0. If you imagine an original number of 10 billion, you would get 1 over 10 billion and a very, very small number, which would still be higher than 0, just not much. Conversely, if you take a fraction, let's say a half, a proper fraction between 0 and 1, when you reciprocate a fraction, you get 1 over a half, and you know from dividing fractions to invert and multiply by the bottom number, so we end up with 2. And if we reciprocate a quarter, by the same logic, we're going to end up with 4. So if I reciprocate 1 over 10,000, I'm going to get 10,000. So reciprocating a proper fraction, as the proper fraction shrinks and shrinks and shrinks, is going to give you a larger and larger and larger number when you reciprocate it. So let's apply that knowledge to this graph and see what results. So in step 1, all your x-intercepts of your original function become vertical asymptotes. I have 2 x-intercepts on this graph, one at 3 and one at negative 1. Those x-intercepts both have a y-coordinate of 0, and we are reciprocating the y-coordinate. That's the overall idea to keep in mind. So when I reciprocate 0, I get 1 over 0, which is undefined. So what happens is at that x value, we get a vertical asymptote for each of our x-intercepts. On the next slide, you'll see a nicer version of this printed out. But that's step 1, find any x-intercepts and change them into vertical asymptotes. There they are, drawn much more nicely than I can. In step 2, all points that have y-coordinates of 1 or -1 are invariant points, which means they do not change from the original graph to the reciprocal of the original graph. Again, because you're reciprocating the y values, reciprocating 1 just gives you 1, and reciprocating -1 leaves you with -1. So those points have the same y value after reciprocating. So those points are, let me change my color here. Here's a point with a y-coordinate of 1 and -1. Here's a point with a y-coordinate of -1 and 1. It's interesting to note that I don't know exactly what the x-coordinates of those points are, and I don't need to. I just need to know what the y-coordinates are to know that they stay put. There's those points again drawn in more nicely in blue. And then for the rest of this, we have to just look at the pattern of how reciprocated numbers behave. So looking at this right-hand third of the graph, if you like, going from this invariant point to the right, we get larger and larger and larger y values. And as we learned on the previous slide, larger and larger y values, when you reciprocate them, become smaller and smaller. They do this fairly quickly on this graph. This point has a y-coordinate of 5. The reciprocal of 5 is 1/5, so that would be approximately here. And as the y values increase, they're going to decrease on my graph, but it's important to note that they won't ever make it down to 0. They come really close, but they don't quite get there. So what we get is a curve approaching the x-axis, but never touching or crossing the x-axis. In this case, the x-axis is a horizontal asymptote. And then in this little bit, kind of squished on this graph, you see y values that are all proper fractions getting smaller and smaller and smaller, approaching 0. So when you reciprocate them, they become larger and larger and larger. Now this is going to be hard for me to graph in without touching that asymptote. You'll see a much nicer version of it on the next page. Okay. The same logic applies here. Our small y values become arbitrarily large, and our large y values become small, but never going down lower than 0. And in the middle here, we need one more point to help us other than these 2 points. We'll use the lowest point of this parabola. It has a y-coordinate of -4. Reciprocating -4 gives me -1/4. So I can put a dot in at approximately -1/4. And then I'm going to join that with the invariant points, and following the behavior of reciprocated numbers, be bound by these 2 asymptotes. This side looks better than this one. So let's take a look at what that should look like if drawn on a computer or by a computer. There's the nice version of it. So again, you can see the light gray was our initial graph. Anywhere the light gray graph had an x-intercept became a vertical asymptote. Any points with y-coordinates of 1 or -1 stayed in the same place. And then as y values became arbitrarily large, they become arbitrarily small, and vice versa. When they become small approaching 0, they become arbitrarily large. Notice that on this graph, our vertical-ish lines do not ever run vertical, and they do not touch or cross the asymptotes. They come very close, but make sure in your work, to avoid mark penalties, that your graph is not touching or crossing the asymptote at any point. And that's all we've got for today. Thanks for watching.